Good afternoon, everyone. I am Chanda Devna, TA of this course named Study Guide in Organic Retrosynthesis and Problem Solving Approach, instructed by Professor Shomik Nanda. So, I am pursuing my PhD from Aizer Berhampur. So, in this classes, I will discuss about some In this class, I will discuss about some name reactions and some different type of organic synthesis, so that which may help you to get an idea about how to plan a retrosynthesis of a large molecule. So before going to the retrosynthesis of a large molecule, you have to know the simple organic reactions so that we can plan the retrosynthesis. So in the first few classes, I will try to cover all the types of important organic reactions. Then in the last 3-4 classes, I will discuss about retrosynthesis of some large molecules by using those reactions. So in the last class, I was discussing about, we started about the rearrangement reaction. So today I am continuing that, so it will be done today. I don't think there is much more left. These are the important ones. So from the next class, we will discuss about some new topic. So let's start. So we are discussing about the rearrangement reactions. So a rearrangement reaction is a broad class of organic reactions where carbon skeleton of a molecule is rearranged to give a structural isomer of a original compounds. So there are different type of rearrangement, like that is 1,2 rearrangement and 1,3 rearrangements. Here are the examples. In the last class, I have already discussed about the Beckmann rearrangement, pinnacle rearrangements. So in the today's class, we will discuss some of the remaining ones, and I think all will be almost come. This fries will be remaining because this is different. This 1,3 rearrangement. I will discuss this in the next class. I mean, Beckmann has been discussed in the last class, pinnacle. Today I will discuss all these three and this Claisen. So the fries will be remaining, that we will discuss in the next class. So what is Claisen rearrangement? This is one of the important one because it has been seen in NET and GATE examination. Almost an alternative year we get a question from this Claisen rearrangement. And also, as this reaction requires no heat, just no reagent, just heating. That's why it's very easy to apply for different kind of substrates. So Claisen rearrangement, Claisen is a powerful carbon-carbon bond forming chemical reaction. The heating of an allyl vinyl ether will initiate a 3,3 sigma-topic rearrangement to give a gamma delta unsaturated carbonyl compound. So there are various type of Claisen rearrangement, aromatic Claisen, Bayes Claisen, Eastern-Moser, Photo-Claisen and Johnson-Claisen, and there is also Ireland Claisen reaction. So what is aromatic Claisen? So first just see the mechanism. This is 3,3 sigma topic reaction. So that's before that we have to if we number this one along this single bond, both are like 1 1. So these are kind 2. So as oxygen is more electronegative, so bond will break towards the oxygen. So this is called 3,3 sigma topic reaction, and we get this as a product. So if we apply this in case of aromatic system, this is called aromatic Claisen rearrangement. Suppose one of these double bond is part of a benzene ring, then it goes through like this way, as so it will break towards the oxygen atom. sorry. We'll get this as a product. Then after that it undergoes aromatization. And this is our product. Next is Bellus-Claisen. What is Bellus-Claisen? The reaction of a allylic ether, amine or thioether with ketene type of compound is called Bellus-Claisen. So instead of the intermolecular one, if it react with a ketene type of molecule like this one, so there is a heteroatom, forming this as our intermediate. Now the bond breaks along this single bond. So as this is positively charged, so bond will break. Okay, so we get this as our product. Next is Eschen-Moser-Claisen rearrangement. In this reaction, the allylic alcohol in presence of N dimethylacetamide and dimethylacetal to form gamma delta unsaturated amide. So here in this it undergoes a trans-esterification type of reaction. One OMe left from the system, and again another molecule of OMe leave by this adjacent H atom. This comes here. This leave from the system, forming this as our one of the intermediate. Then after that it undergoes a Claisen reaction and form this as our product. Next is Johnson-Claisen. So similar to this Eschen-Moser, it undergoes a trans-esterification where this OH will attack to this carbon center and eliminate one of the OMe, and then another molecule of H will be removed and eliminate one of the OMe, forming this as a one of our intermediate. Then it undergoes Claisen rearrangement, forming this as our product. Okay. The next one is Ireland-Claisen. When you use a allylic carboxylate with a strong base to give a gamma delta unsaturated carboxylic acid, the rearrangement proceeds via silyl ketene acetal, which formed by trapping the lithium enolate with chlorotrimethylsilane. Next is Aza-Claisen rearrangement. When this Claisen rearrangement occurs in case of heteroatom rather than oxygen, instead of oxygen is with nitrogen, it is called Aza-Claisen rearrangement. This comes here. So in presence of a strong base, this proton is deprotonated and it comes here, and this nitrogen get neutralized, forming a double bond at this place. After that it undergoes a 3,3 sigmatopic reaction along this single bond and form a new bond here. Okay, so based on all these examples of Claisen rearrangement, we will solve some questions which I have taken from books and some previous year questions also. So let's solve one by one. So the first one is this: they have given this substrate and there is no reagent except heat, and they have asked for which will be the expected product. So I have already mentioned these are Claisen rearrangement, so obviously there will be no such question of any, there will be Claisen rearrangement. You have to just draw the arrows. So I just give 2 seconds, just think what will be the product of this reaction. So let's try. So we have to just perform a 1,3,3 sigmatopic reaction. So if we just give the numbering, so the correct option will be option B. Okay, now the question is, it will be option B or option D, because in both of the cases the product is same, there is a just change in the stereochemistry. So the see, if the double bond is E, so the correct option will be option B. Okay, let's go to the next one. What will be the product of this reaction? So from this structure, and also as the topic is Claisen, so it will, you can see this will undergo the Claisen rearrangement. So just move the arrows. It is simple one. Sorry, it will be like this. Okay. So the correct option will be, so the option of answer will be sorry. Okay. Let's go to the next question. Draw the expected product of the given reaction. What will be the expected product of the given reaction? So let's numbering first. 1, 1. So the 1 will be along the single bond. Okay. You have to find the symmetry. You have to find the symmetry. Okay. So if you just move like this way, so the correct option will be, there will be a ketone, there will be a bond, new bond, and a ketone, sorry, aldehyde center here. There is a new bond, along that place there is a methyl group, and like this will be our product. So the correct option is option B. The correct option is option B. Okay. Let's go to the next question. What will be the answer of these two? I just give 5 seconds, just think. So it's only 1, 1, 2, 3. If you just draw it in a cyclohexane pattern, is a double bond, so it will be break this way. Okay, so this will be the product of this reaction. Okay, let's try this one in similar way. So the answer will be, it will be connected from this place. There will be two chlorine, adjacent to that there will be a ketone, sorry, aldehyde. So this will be our product. I hope you are getting it. This will be our product. What will be the mechanism of this reaction? What will be the mechanism of this reaction? I just give 5 seconds, just think. What will be the mechanism of this reaction? So let's draw it. So if we just give the numbering, it will be like this way. Okay, so let's draw it. This undergoes a simple aromatic Claisen reaction. So the product will be, from the first instance, the product will be this. Usually in case of this type of aromatic Claisen, we perform this Claisen reaction, and after that this it loses its aromaticity, and after that there is a proton at this ortho with respect to this keto position, and this ortho hydrogen, eliminates to give its aromatization back. But in this case, both the ortho positions are occupied with a methyl group. Both the ortho positions are occupied with a methyl group. Therefore, there is no hydrogen available to regain the aromaticity. These type of compounds are not stable according to Hooker's law. The aromatic compounds are highly stable, so this reaction will not proceed, but this reaction takes place. So that means somehow it will regain its aromaticity. So therefore, if you know about Cope rearrangement, it is similar to Claisen, a similar type of 3-3 sigma topic rearrangement, but in case of totally carbocyclic ring. Cope rearrangement is when this Claisen rearrangement occurs in case of carbocyclic ring, means totally carbon atoms are there, that is called Cope rearrangement. So after a Claisen rearrangement, if as this is not about any reagent, we just need heat for this reaction. This reaction will further undergoes a Cope rearrangement. So what happens here is undergoes a further Cope rearrangement so that it can regain its aromaticity. So this form this it forms this compound. Now there is a H available here to regain its aromaticity, so this moves from here and we get this as our product. Okay, so this is like Claisen followed by Cope. This is a Claisen rearrangement followed by Cope. Okay, the driving force is just to regain the aromaticity. The driving force is just to regain the aromaticity because of unavailability of H adjacent to this keto position, that is adjacent, that is in ortho positions. It will further undergoes a Cope rearrangement so that it can regain its aromaticity. Let's go to the next one. What will be that the terminal sp2 is attached to the benzene ring is 14C mark. Now determine when the product will form, where this 14C carbon will be labeled, which carbon will be 14C. So this, if this carbon is 14C, now they are asking after formation of the product which carbon will be 14C mark. Now this, in this substrate the terminal carbon is 14C. The terminal carbon is isotope labeled. So after the formation of the product, which carbon will be isotopically labeled. So this is the simple Claisen reaction. So the product is this is isotopically labeled. As there is already a H atom at this ortho position, so there is no scope of Cope rearrangement. It will undergoes a aromatization. Forming this as our product. Okay, let's go to the next one. So here, which carbon will be isotopically labeled? This internal carbon. This become isotopically labeled. They have asked what will be the structure of A and B. What will be the product A and B? So if you add a strong base, it will obviously strong base will take a highly acidic proton. So this proton is highly acidic, so it will generate this O minus hydroxyl phenoxide anion. So this will be our A, and Na plus will be counted to this. So this will be our A. After that they will get a Wilkinson product. Wilkinson product means just etherification. So this O minus will attack to this, it will be a allylic substitution. Okay, so this Wilkinson product will be formed. After that it undergoes a Claisen rearrangement like we have done, then simple aromatization. Okay, this is the example of Ireland Claisen reaction. So they have asked, suggest the mechanism of the first step, predict the product B, and hydrolysis of B, so suggest the mechanism of forming this acid from B. This is the example of Ireland Claisen. I have already explained what is Ireland Claisen. I just give 5 seconds. Just try once. Okay. So they have asked for the mechanism for the first step. So if you add LD is a strong base, it will take a proton from this alpha position. This, it will form a negative center here, and this enol undergoes a tautomerization and forming an enolate. Forming an enolate here. In the next step, this O minus will attack to this TMSCl, and this TMS group will be entered, forming this A. Okay. Then after that it undergoes a Claisen reaction. So the product will be OTMS here. And there's a new bond formation at this place and a double bond here. After that, if you add H plus, this OTMS will be hydrolyzed, forming an acid. So this will be our product. Okay. So if we answer one by one, first the mechanism of the first step that we have shown already is goes through a enolate mechanism. After that, predict the formation of product B. So this is our product B. And what is the mechanism of formation of carboxylated? This is simple hydrolysis reaction. Simple hydrolysis reaction. If you want to see the mechanism, it will be like if you we just draw the TMS in a so this water molecule will attack to this silicon center and this will open up, forming this carboxylic acid. Okay. Let's go to the next one. What will be the product of this reaction? So from LDA you can understood from the last one that it will go through a enolate mechanism. Just give it a shot. I just give 10 seconds. So it will go through an enolate type of mechanism. So in presence of LDA it will form an enolate here. Now there is a one thing to know. If LDA is given, it will always form a transenolate. If LDA is given, it always form a transenolate. If LDA along with HMPA is given, it will always form a C-enolate, that is Z-enolate, Z-enolate. If only LDA as a base is given, it will form a E-enolate. And if LDA plus HMPA is used, it will form a C-enolate. So it will form a E-enolate. So if we just give a numbering, so it will form a E-enolate. As silicon has higher molecular weight than that of molecular number than that of atomic number than that of carbon, so this center will be more prioritized, so it is a E-enolate. Okay, so this is by using these two. Next, if you add heat, simple, it will undergo the Claisen rearrangement. So just to know about the stereochemistry of this methyl group, if we just try to draw it via a Zimmermann-Texler transition state. So adjacent there is a methyl group above the plane. OTMS. Whenever there is a formation of cyclohexane ring as a transition state, always go through a Zimmermann-Texler transition state. It will help you to get an idea about the stereochemistry. If there is no concern about stereochemistry, you can draw it by yourself. But if there is a chiral center or a question of stereochemistry, always try to do it via Zimmermann-Texler transition state so that there is no mistake in the stereochemistry of the carbon centers. Okay, so if we just move this one as a trans, so the methyl group is here. So if you just the new compound will be oxygen here, there is a double bond here, and this methyl group is above the plane because it is already from the structure. You can see if you just draw it without Zimmermann-Texler transition state, we won't get an idea. Okay, this methyl group, the newly methyl group will be above the plane or below the plane. But here you can easily see to get to remaining the, as it is a concerted reaction, there is a no ring bond rotation in during this course of the reaction. Because of that, this reaction takes place in single step, so that from maintaining the trans stereochemistry along this double bond, it will, this methyl group is shown towards the above the plane. So when the bond forms, it keeps above the plane. Okay, newly formed bond, it remains above the plane. If you just draw it like this way, it will be, I think, better for you to understand. Let's go step by step. So this goes here and this attacks to this place, so it will form newly, there is a double bond here, and from the methyl group is along this side. So if you just draw the methyl for C, there is a trans stereochemistry. It is easily, you can get an idea. Otherwise it is very problematic. There is, you don't have to think much, just move the arrows. So it will be a trans stereochemistry here, and this methyl group is already above the plane, so this will be above the plane, and there is a OTMS here. Next step, as H3O plus is given, so it will be acidification will be, it will be acidified. So okay, so this will be the structure of the product. Okay, so always go to a Zimmermann-Texler transition state. You know now what is the 6-member cyclohexane transition state are called Zimmermann-Texler transition state. So let's do they have given a ET3N. So in presence of base, this undergoes a esterification reaction. So this ET3N will attack here first, and this will get removed, and another molecule of ET3N will take a proton from here, and it will generate a negative center on the oxygen atom, and this will again remove the ET3N and will form a ester. If you add in the next step, if you add LDA and TMSCl, what will happen? In the similar way, there will be a double bond at this place and it will be OTMS. Now it's a substrate of Claisen reaction. So this will just, this goes here. So the product will be so after hydrolysis, the product will be this. Just draw by yourself. I think you will understand. Now we have already done much questions, and as there is no concern of stereochemistry, we are not drawing it via Zimmermann-Tuxler. If in your product they asked for the stereochemistry of this isopropyl group or this alkyl center, you have to draw this via Zimmermann-Tuxler transition state, so to avoid any kind of such mistake. I am not drawing, just for a practice, just take this question and draw it through a JT transition state, so that you will get an idea how to draw the transition state, and you will get an idea what will be the stereochemistry of these two chiral center. These two chiral center. Just draw it by yourself. It's kind of a homework. You can draw it by yourself and get an idea. If any doubt is there, you can contact me. I will give you the answer. Next is this one. So this is a example of Johnson-Claisen reaction, which we have already discussed. So it will undergo the first a trans esterification. It will goes here and remove one of the OET group. Then this H will be eliminated and remove another molecule of OET group, forming this as our product. After that, if you give heat, it will undergo the Claisen rearrangement. So this bond breaks here. So the newly formed product is this ester. Okay. Let's go to the next one. This is an example of this type of Johnson-Claisen. NME2. Okay, so it will be a next step, heat is given, so obviously there will be a Claisen reaction. As stereochemistry is a concern here, they have already shown a stereochemistry of the chiral center, so it will be better if we draw it via Zimmermann-Texler transition state. So this is the NME2 group here. Next is there is a this double bond is trans, so obviously this methyl group will be above the plane, kind of will be trans like this way. Okay, and there is a phenyl group adjacent to this which is above the plane, so I am drawing it like this way. Now if you just move the arrows, it goes here, this attacks to this carbon center, and this double bond moves, so the product will be like this. Now as phenyl is above the plane, just we are drawing the similar way. See, it's so easy if you draw via this type of transition state. So, and this methyl group was like this, so here it will be already above the plane. And there is a oxygen has a NME2 group here. Okay, so here you can get idea. So the newly formed double bond will be Z E in stereochemistry, and this methyl group will be above the plane. So whenever there is stereochemistry is concerned, always go through this type of transition state. Next is Hoffman rearrangement. So what is Hoffman rearrangement? We have in the last class we have already discussed about Beckmann rearrangement. It is kind of similar. Uh, it's kind of similar. So in this reaction of bromine with sodium hydroxide forms a sodium hypobromide in situ, which transforms a primary amide into a amine through a isocyanate intermediate. So if you see the mechanism, they have taken amide. If you add a bromine in this one, if you add first they have added NaOH, the sodium hydroxide, it will take a proton from this amide nitrogen, then bromine is added, this N minus will attack to this bromine center and one bromine will be eliminated, and after that it will form this hyperbromide, and next if you another, as OH minus is already in the system, this another molecule of proton will be eliminated, and through this rearrangement it will form this isocyanate intermediate, and if you add water in the reaction it will form this carbamic acid, and through elimination of carbon dioxide it gives us this amine. Instead of water, if you add methanol in this step as a solvent, what will happen? Then methanol will attack to this carbon center and it will open up, it will form a ester, carbamic ester. It it will form a carbamic ester. Okay. So this, as via this reaction we can easily transform uh, amide to amine. This is one of the important one in case of synthesizing different type of drug molecule as well as natural products, because we know that nitrogen is a very important molecule, and inserting a ammon NH2 in a group is very difficult. So in this way you can do it very easily. The next example is Cartier's rearrangement. This is similar kind of reaction, as this is going through a same intermediate, that is isocyanate intermediate. Here instead of bromine we are just using N2 as our leaving group instead of bromine here. Just try to see the similarity so that you have to remember less number of mechanism. If you can correlate a multiple reaction by a simple one mechanism, it will be easier for you to attempt more questions. So try to connect the different type of name reaction by a single mechanism. Whichever has similar type of mechanism, just try to remember the one and try to draw the difference between all this, so that by just remembering one mechanism you can attempt all the questions. So just see, instead of bromine here as a leaving group they have used N2, so that the similar way this N minus, this double bond shifts here, and sorry, there will be R group in this carbon center system and forming this isocyanate as a product. So both the reaction gives a similar type of intermediate, so the result will be also same. The result will be same, as both the reaction give a similar kind of intermediate. So let's try these questions. What will be the product of this one? This is going through a Hoffman rearrangement. So if we just try to draw the product directly. So in case of Hoffman rearrangement, what happens? This, from amide we get amine. So the remaining part, the R group, if you are drew it through a mechanism, just for the first one I am just doing the mechanism. So it goes through via this. So when this proton get deprotonated via base, this proton get deprotonated via base, this negative charge moves here, and this total R center again come back to here, and this bromine leaves from the system. So see, this total system comes, and so there is no change in this R. There is no change in this R. So from here also you can directly draw the product. Just keep the R part same and just remove the carbonyl and draw the NH2. Okay. See, this will be our product. There will be no change in the stereochemistry. You will just remove the CO group from the system. In the same way, if you do this one, it will give. Now you have to see, just notice which type of solvent they are used. Here they have used acid, water. That's why as a product we get a carbamic acid, and through decarboxylation we will get amine. Through decarboxylation we will get amine. But if any alcohol is given, there is no question of decarboxylation. So just always notice which solvent has been used. If it is not water, there is no question of formation of amine from amide. There is no question of forming amine from amide if water is not given. So it will form this carbamic acid. This moves here. Okay. Now in this case you have to see there is methanol is given, not the water. So what will happen after the isocyanate step? Methanol will attack, so it will form a methyl carbamate. It will form a carbamate. Okay. So always notice the N to remove from the system and forming this isocyanate as a product. So both the reaction gives a similar type of intermediate. So the result will be also same. The result will be same as both the reaction give a similar kind of intermediate. So let's try these questions. What will be the product of this one? This is going through a Hoffman rearrangement. So if we just try to draw the product directly. So in case of Hoffman rearrangement, what happens? This from amide we get amine. So the remaining part, the R group, if you are drew it through a mechanism, just for the first one I am just doing the mechanism. So it goes through via this. So when this proton get deprotonated via base, this proton get deprotonated via base, this negative charge comes moves here, and this total R center again come back to here, and this bromine leaves from the system. So see, this total system comes, and so there is no change in this R. There is no change in this R. So from here also you can directly draw the product. Just keep the R part same and just remove the carbonyl and draw the NH2. Okay. See, this will be our product. So there will be no change in the stereochemistry. You will just remove the CO group from the system. In the same way, if you do this one, it will give. Now you have to see, just notice which type of solvent they are used. Here they have used acid, water. That's why as a product we get a carbamic acid, and through decarboxylation we will get amine. Through decarboxylation we will get amine. But if any alcohol is given, there is no question of decarboxylation. So just always notice which solvent has been used. If it is not water, there is no question of formation of amine from amide. There is no question of forming amine from amide if water is not given. So it will form this carbamic acid. This moves here. Okay. Now in this case you have to see there is methanol is given, not the water. So what will happen after the isocyanate step? Methanol will attack, so it will form a methyl carbamate. It will form a carbamate. Okay. So always notice which solvent has been used. So this is an example of Cartier's reaction. So what will be the product? What will be the product? Suppose first of all there is multiple chiral centers are there, five chiral centers. So first you have to determine here I am saying that is a Cartier's reaction. You have to see, pick up the points from where you will decide it's okay, it is a Cartier's reaction. First of all, there will be a carbonyl azide group, carboazide group, if this type of group is there, and also in this case there is a question of formation of Cartier's rearrangement. So obviously this this total R part will be same, no change of this all this stereochemistry, no change in all this stereochemistry. So all this will be same. I'm not drawing all this chiral center will be as same as the substrate. Next what will happen? This will be above the plane. It will form this isocyanate intermediate. Mechanism I am not showing because I have already discussed multiple times. So just to do this by yourself, you will get an idea. After that, now see what type of solvent they have used. There is no water, no alcohol, but they have had acetic acid. So acetic acid will attack to this place. So the product is, I am not drawing all the chiral centers. It's not like that all are gone, okay? All four are there with the same stereochemistry as the substrate. I am not drawing it because of simplicity. So the product will be NH OAC. Okay, I hope it's clear. It's very easy. Now there are two applications of this Hoffman rearrangement. First, we can synthesize anthranilic acid from phthalimide. So and next one is we can form nicotinamide. We can convert nicotinamide into 3-aminopyridine. We can convert nicotinamide into 3-aminopyridine. So one I will do here, and one I am keeping, so that you will search from this for this name what is nicotinamide and what is 3-aminopyridine. 3-aminopyridine is like pyridine and 3 position there is amine. What is nicotinamide? So this one is kind of for you guys to practice. I will show the answer in the next class. So I am just show the preparation of anthranilic acid from phthalimide. Do you know the structure of the phthalimide? If you know the phthalic acid, and from that there will be amide. So phthalic acid means 1,2-dicarboxylic acid. 1,2-dicarboxylic acid. So phthalimide will be the amide version, phthalic anhydride, and that amide version of that one. So this is called phthalimide. This is our phthalimide. Now, do you know what is the structure of anthranilic acid? 2-aminocarboxylic acid is known as a anthranilic acid. 2-aminocarboxylic acid is known as a anthranilic acid. This is one of the important compound in case of drug synthesis. You know about anthracene? So it's from anthranilic acid only. So this is 2 amino benzoic acid. This is called anthanylic acid. So how we'll get this anthanylic acid from this phthalimide? So let's go step by step. If you add a base in this one, this center will be hydrolyzed. It will give opener and form this acidamide, 1,2 acidamide. The next step. Now what is the difference between these two? Just there is a amide and but there is a amine. So what is the procedure for making amine from amide? Obviously Hofmann degradation or Hofmann rearrangement by using water as a solvent. By using water as a solvent. So how can I get this as a product? If you add Br2NOH in the first step, and the second step, if you add water as a solvent, you will get anthanylic acid as our product. It is very easy. So for your practice, just try this last one. So this much for today's class. I will just give an overview what I have discussed. So today we started with Claisen rearrangement and different type of Claisen rearrangement. Then we solved some questions based on this different type of Claisen, and we solved all the mechanisms. I hope you get an idea how to determine the stereochemistry of the chiral center and also as well as the newly formed double bonds. So it's go through a Zimmermann-Tuxler transition step. Then we discuss about Hofmann rearrangement followed by Cartier's and solve some questions based on that. So I hope you have understood. So thank you everyone. We'll meet in the next class. Have a nice day.